This study provides the first global-scale assessment of deep sediment core contamination using data from rural western Serbia. The region, lacking active mining and major industrial activity, offers a unique setting to evaluate natural and anthropogenic influences on soil chemistry. While contamination levels are moderate, the findings underscore the importance of monitoring subsurface environments, as changes in land use or hydrogeological conditions could mobilize toxic elements and pose risks to soil and groundwater systems. A total of 250 sediment samples from 18 boreholes, ranging from 5 to 58.5 meters in depth, were analyzed. The cores, composed mainly of quartz and clay minerals, were examined using energy-dispersive X-ray fluorescence spectrometry to determine concentrations of 11 major oxides and 21 trace elements. Additional analyses included carbonate content, organic carbon, and grain size. Elevated concentrations of vanadium, thallium, and barium were consistently detected, exceeding local and international safety thresholds. These levels were largely attributed to geogenic factors such as parent rock mineralogy and sediment-forming processes. Vertical distribution patterns revealed that groundwater movement and clay retention capacity strongly influence element mobility and stabilization. Once deposited, many elements appear geochemically stable, preserving long-term records of natural and anthropogenic inputs. Histograms of barium, vanadium, and thallium concentrations highlight their statistical distribution. Barium shows a wide skewed spread, with many samples surpassing remediation thresholds, suggesting localized contamination. Vanadium concentrations are symmetrically distributed, generally above regulatory limits but below remediation concern. Thallium, though limited to 0 to 10 micrograms per gram, displays a sharply peaked distribution near critical thresholds, underscoring its environmental relevance due to toxicity at trace levels. Vertical distribution analysis shows contrasting behaviors among trace elements. Thallium, cadmium, zinc, and selenium exhibit higher mobility and are concentrated in surface horizons due to atmospheric deposition and anthropogenic inputs. In contrast, vanadium, barium, nickel, chromium, and cobalt display low mobility, being retained by clay minerals and accumulating in deeper sediments. Lead and copper, though influenced by human activity, remain immobilized in upper layers due to strong binding with organic matter and mineral phases. Clay-rich subsoil and deep layers act as natural barriers, limiting vertical migration and preserving geogenic associations. This stratification highlights the importance of mineral composition and redox conditions in controlling contaminant mobility and long-term retention. To evaluate contamination and risk, several indices were applied. The contamination factor measures concentrations relative to baseline levels, while the enrichment factor compares target elements against references to detect deviations from natural background. EF analysis revealed enrichment of arsenic, lead, mercury, and cadmium, suggesting historical anthropogenic input or geochemical anomalies. Although concentrations remained within regulatory limits, elevated EF values imply potential long-term concerns if land use or environmental conditions change. The pollution load index averaged 0.8, indicating baseline contamination without significant pollution. The potential ecological risk index averaged 133.5, classifying the area as having moderate ecological risk.